GPT-3 has gotten a lot of attention recently. So I got curious and I want to dig a little bit deeper and understand what exactly GPT-3 is, how it works, what it's doing, but also how it compares to other NLP models that I use on a pretty consistent and regular basis. I'd like to share some of what I've learned with you all, and hopefully by the end of it, you'll also have a sense of how exactly GPT-3 works, what it's good at, what some of its limitations are, and how it compares to alternative models. And there's been a lot of models over the last couple of years, and this is a good thing. It's a good thing because we've seen a pretty radical change in state-of-the-art in natural language processing. But all of these models, BERT, RoBERTa, GPT, XLNet, they all have a few things in common. First of all, they're all language models. That means at their core, they're looking at raw text and trying to learn something just by looking at the raw text. Because presumably the words that we use and the way that we arrange words conveys meaning. So if we can train a model, a machine learning model, to extract the meaning from the words and the grammar, then well, that would be a good thing. And it's turned out to work quite well. Now, the other thing that all of these models have in common is that they're all based on transformers. Now, a transformer is the specific neural network architecture that has been implemented in all of these models, starting from BERT through GPT and all the ones in between. And the idea of transformers is that they use this thing called attention. So the model looks at sentences and it plays these games with sentences by looking and paying attention to different parts of the sentence to try to understand and extract meaning and insight from text. So although all these models have these things in common, there are two general families that we can slot these models into. On the one hand, we have the BERT and the RoBERTa and the Albert family of models, which for obvious reasons I'll call the BERT family. These are bi-directional encoders. And there's a fundamental difference, subtle but fundamental difference, between the BERT family of transformers, the BERT family of models, and GPT and XLNet and this other family. And the second family that GPT falls into, they're called autoregressive decoders. Now the best way to see the difference is graphically. So here's a picture which I've taken from a blog that's linked at the bottom. It's a very good blog to understand how these models work. I highly recommend you go there and visit that blog. But from a high level, models like BERT and the BERT family, they're shown on the left. And these are bidirectional encoders, which means that when you give BERT a piece of text, BERT will look at that entire piece of text from left to right, from right to left. And as it's looking at any one particular word, it will look at the surrounding words for context. So if I take the example sentence, I'm going to throw a ball to the outfielder. Well, BERT will take that sentence, and if I focus in on the word ball, well, when it's trying to encode or embed that word, it will know that I am throwing the ball, and it will look at the other side of the word and also get that context. So it will know that I am going to throw that ball to an outfielder. Now, let's contrast that situation with the situation on the right. And the situation on the right, this is the GPT style of family. If you give a GPT or similar models that same sentence, it's not going to look at all the context to the left and right of the word ball. It's going to start at the beginning and say, I am going to throw a ball, and then GPT tries to predict what's going to come next. That's its language learning task. All it's doing is trying to predict what word comes next, and it turns out that's a pretty good way to learn a language and to extract information from language. And that's all GPT is trying to do. Now, of course, there's some downsides. So for that example sentence, when I get to the word ball, GPT doesn't know whether I'm going to throw the ball to an outfielder or to a wide receiver or to my daughter in the backyard. It tries to guess these things, and it does a pretty good job. But on the other hand, this is where you see a lot of attention, no pun intended, around GPT-3, is that it's really good at writing. It's really good at generating text because it was trained to guess the next word. And so if you give GPT a sentence like, I'm going to throw the ball, well, GPT has seen enough examples that it can fill in the blanks. It can fill in the rest of the sentence, fill in the rest of that sentence in several ways that make sense. And so again, to reiterate, that's why a lot of the attention around GPT-3 has been its uncanny ability to write things like news articles, even code. And this is pretty impressive, and it's pretty remarkable. Now, the big thing with GPT-3, apart from its impressive performance at writing and generating text, is its size. And the author's right, each increase in model size has brought improvements in text synthesis and or downstream NLP tasks. So in other words, looking back at the recent history of transformer models, they've noticed that we add more parameters, make the models bigger, they tend to work better. So effectively, GPT-3 is an experiment to see if we can extrapolate off the end of that curve and make a really big model. And we'll see if that really big model does really well. How far can we take this size argument? So to give you a sense of how big is in the context of GPT-3, let's look at a few examples. I'll start with BERT. BERT had 340 million or so parameters, which is a lot of parameters. And you know, a parameter is the most granular part of a model. It's the smallest bit of a model. The more parameters, the bigger model, the more capacity it has to learn. Now let's look at RoBERTa, which was an extension of BERT, but roughly the same size, about 355 million or so parameters. Now if we look ahead to GPT-2, GPT-2 was quite a bit bigger, over 700 million parameters. Similar to that was T5, again between 700 and 800 million parameters. These are big models already, but how big did GPT-3 go? Huge. GPT-3 clocks in at 175 billion parameters. It's a big model. Now, to show this on a slightly more equitable chart, we can go to a log scale. So we're looking at the number of parameters, log number of parameters on the vertical scale now. But even here, you see that GPT-3 is about 3 orders of magnitude larger than the models that came before it. Now these numbers, it's hard to get an intuitive sense of how big 175 billion is. But kind of an interesting thought experiment is, well, what if I take one parameter and equate that to a unit I'm more familiar with, like 1 second? So if one parameter in one of these models equates to 1 second, then both BERT and RoBERTa come out to be roughly 10 years of time equivalent. The next two larger models, GPT-2 and T5, if one parameter represents 1 second, then those models come out to be about 24, 25 years. But now with GPT-3, with 175 billion parameters, that would be over 5,000 years if one parameter equaled 1 second. It's a lot bigger. GPT-3, in fact, takes supposedly 320 gigabytes of memory, and it costs $12 million to train. So GPT-3 is a very large model, but what does it actually do, and how is it different than the BERT family? Now, a few slides ago, I showed you kind of the structural difference between GPT and the BERT family of transformers, but what I'd like to get into now is how it's functionally different, perhaps even philosophically or conceptually different. And I think one interesting way to unpack this question is simply through the titles of the papers that came out describing these models. So with BERT, the title of the paper was BERT, Pre-Training of Deep Bidirectional Transformers for Language Understanding. And I think the key word that I want to focus on here is pre-training. That's always been BERT's MO. You start off by pre-training a generic model. So this is a transformer that understands language well. It has smart embeddings for words, but it's not useful for anything yet. You have to start off with that pre-trained model, but then take it further and fine-tune it to do some specific task. So for example, you might take a pre-trained BERT model, but then fine-tune it to do text classification, or fine-tune it to do question answering. You might fine-tune it to do sentiment analysis or named entity extraction. The idea, though, is starting with a pre-trained generic model and specializing that model in any number of directions. GPT-2 and 3 seem to have a slightly different objective in mind, however. So the GPT-2 paper was titled, "Language Models Are Unsupervised Multitask Learners." So if you notice, the emphasis is different. I think the operative word here is multitask learners. Their approach was to posit that a language model could be pre-trained, but also be good at performing multiple tasks more or less out of the box. They were not interested in fine-tuning GPT to be really good at one thing or another thing, at least not necessarily so, but they were more interested in the fact that this could be good at several things without fine-tuning. And that thread was carried on to GPT-3. The title of the GPT-3 paper was "Language Models Are Few-Shot Learners." And so we'll get into what few-shot learning means. But the idea is that you have a pre-trained model that is right out of the box, right off the bat, good at several different tasks. Now, how does it do this? One way to describe this is to break the training into two different parts. The top part, which is shown in purple and is called the outer loop, and this diagram, by the way, is out of the GPT-3 paper, is kind of your standard language pre-training. BERT does this and GPT-3 does this. And this is learning via gradient descent during unsupervised pre-training. This is where you're just learning the model. With BERT and the BERT family, it tries to fill in blanks. That's the game it plays to learn the language. With GPT-3, as we mentioned earlier, it's trying to predict the next word. But it's still unsupervised pre-training. It's not necessarily task-specific training. These models, after completing the outer loop, they're not really good at anything in particular, right? Well, GPT-2 and 3's position was that even stopping with that pre-training, we can follow it on with something called an inner loop. And this is not done during training. The inner loop is at runtime. It's when you have your pre-trained model, can you take a model and show it a few examples of what you would like it to do, and then have it learn on the fly to do these different things? So this is specific to GPT-3. BERT, again, as I said, does not take this approach. Let me show you a few more concrete examples to help clarify this. An approach like BERT and the BERT family of models, if we want to translate a phrase from English to French, we'll have to show BERT multiple examples of translation from English to French. And after every example, every batch of examples, BERT will update its model parameters through the gradient update. And so as we're going through these examples and BERT is learning, it's updating the model, and this model is becoming an English to French translation specialist. All the parameters in the model are adjusting themselves specifically to this task, and it can actually get pretty good at that task. That's BERT. GPT-2 and 3, as I mentioned, have a different approach. We'll start with zero-shot learning. The idea here is, can I take a GPT-3 model that has just been pre-trained, not specialized like BERT, but can I give it some task and just tell it what I want to do at inference time, at runtime? So I'm going to say, hey, GPT-3, I want to translate English to French. So here's cheese blank. And I want GPT-3 to be smart enough out of the box to know what I want to do by reading what the task in the input and then doing that automatically. This is called zero-shot learning because GPT-3 has never seen an example of English to French translation. I'm just telling it what I want to do at the input and asking it to do it automatically. Contrast this with one-shot learning. With one-shot, it's the same idea. I'm going to take the GPT-3 model and say at input, not during training time, but at input time, hey, take this, translate English to French. And I'm going to give you one example. Here's your one shot to learn what I want you to do. Sea otter maps to, I'm not going to try to read French, but there it is. Now, after GPT-3 sees that one example, I want to fill in the blank in my real example, which is translating cheese to French. Can GPT-3 do that? If it does, that's an example, a successful example of one-shot learning. Again, I'm going to say this a couple of times. This is the big difference. GPT-3 is not fine-tuned to translate English to French. I'm telling it what I want to do after it's trained, in this case giving it one example and expecting it to take it from there. Now, in reality, it might take more than one example. So you'll hear the phrase few-shot learning. It's the same idea. At input time, at runtime, at inference time, I'm going to say, hey, GPT-3, translate English to French, but now I'm going to give you a couple of examples. So here you see 3 examples of English to French translation. And then on the last one, I give it the English and I ask GPT-3 to fill in the blank. It turns out it's pretty good at this. This is a chart that's, I took it out of the GPT-3 paper. There are a lot of these kind of charts. I picked this one just as a typical example. But what you see is along the bottom axis, you have the size of the model in billions of parameters. Again, testing this theory of bigger is better when it comes to model performance. And so let's stay all the way out here on the right, which is 175 billion. That's the largest model they trained. These horizontal lines at the bottom, you see random guessing. Up here, you see a couple of BERT models. And up here, you see kind of state-of-the-art and human performance. And all of these are measured on the superglue score, which is an NLP benchmark. So the blue line is zero shot. I don't show GPT-3 in examples, and I just see how well it can do on this variety of NLP tasks that's measured by superglue. And surprisingly, it does, well, not horribly, better than random guessing. But what's really interesting is if I give it one example, I give it one shot. or a few shots, which in this case is I give it 32 examples and then I ask it to take it from there, GPT-3 does quite well. It's competitive. Actually, it beats a little bit fine-tuned BERT. And again, just to reiterate this, in this case, that fine-tuned BERT was specifically trained to do those tasks as well as it could. GPT-3 was just a generic pre-trained big model and then given a few examples and then asked to take it from there. So the fact that it's competitive with a few shots is interesting and impressive. So what tasks were actually tested? There's a variety of them. You can read about this in the paper. It's a very well-written paper. But GPT-3 was tested on things like sentence and paragraph completion, which is, you would think it would be good at because that's what it was trained on. That's what it was trained how to do. But it was also asked to do things like question answering, translation, as we've seen, pronoun reference resolution, which can be, quite tricky. And then some, you can read the list here. And there's also synthetic demonstrations that I think are fun and interesting. So to give you an example of one of the synthetic demonstrations, I think highlights how potentially impressive GPT-3 is. This is an example from the paper. But we're going to give GPT-3 a new word, a made-up word, a fictional word, but we're going to ask GPT-3 to use it in a sentence. So again, how do I tell GPT-3 that I want it to do that? Well, I have to give it an example first. So in gray here is the example I give to GPT-3. I'm going to say, hey, GPT-3. A Watpu is a small furry animal native to Tanzania. An example of a sentence that uses the word Watpu is, we were traveling in Africa and we saw these very cute Watpus. Now, I continue and say, now to do a farduddle means to jump up and down really fast. An example of a sentence that uses the word farduddle is, and then I ask GPT-3 to give me an example of this made up word that I just defined for it on the fly. And GPT-3 says, one day when I was playing tag with my little sister, she got really excited and she started doing these crazy farduddles. That's pretty cool. I gave it the definition of this word at runtime and it gave me a very coherent and reasonable sentence that uses the word correctly. So this is an example of a couple of things. GPT-3, was it good at? It's pretty good at text generation. And it's also, which is one of the main arguments of the paper, good at learning just from examples without fine-tuning. So the $12 million question is GPT-3 a child prodigy or simply a parlor trick? Now the child prodigy analogy, I saw it online. It's not original to me. I saw it on a blog somewhere. But the idea is, for example, I'll play this game with my daughter where I'll say 5 times 10 is 50, 6 times 10 is 60, 7 times 10 is 70. So what's 8 times 10? And I want to see if she can pick up the pattern and extrapolate off of it. And that's basically what GPT-3 is doing, which is impressive. On the other hand, is this just kind of a neat trick? Most of the examples that we see online are of GPT-3 writing. It's generating text. And it turns it is good at that. It was trained to generate text. It was trained to write text. So for example, I give it the headline of an article and it completes that article. Now, not all the articles it writes are going to make sense. And in fact, you don't have to look too closely to find some holes in logic or just see some bad examples where things don't make sense. On the other hand, how often do I need a 175 billion parameter model to write a news article for me? All things considered, there's still a few practical considerations, regardless of which side of this choice that you come down on. One of them is obviously the issue of size, and the authors acknowledge this in their paper. They say a limitation associated with models at the scale of GPT-3, regardless of what you're trying to do, is that they're both expensive and inconvenient to perform inference on. So yeah, with a model this size, I'm going to need multiple servers. I'm going to have to distribute the model across multiple GPUs. It's going to be a headache to run jobs on. And not to mention just the expense of either buying or renting that hardware. And it's a huge model, so it's going to take a long time to even run data through it. And so it's big, but that makes it also unwieldy. And the last thing that I would mention, and I think this is one of the big issues for me, I do think GPT-3 is very impressive, but is it what I need? And the answer is probably no. In my day-to-day work, I want a model that's really good, usually, at doing one particular thing. If I want to do text classification, I want to take a model and adapt it to the domain that I'm working in and have that model be the best text classification model for that domain that I can come up with. And, well, that's BERT, or at least the BERT family of models. I can fine tune it on the specific language, domain specific language that I'm interested in, and have it be really good at the specific text classification task that I'm interested in. I don't need an all-purpose model. And in fact, going to something like GPT-3, I would have to tell it, I would have to repeat the instructions. I have to give it examples of text classification every time that I want it to classify text, and it wouldn't be as good as a special purpose model built just for that case. And again, the authors acknowledge this in the paper. They say it's really impossible to have, at least at this point, a language system that's the best at everything. Now, on the other hand, although GPT-3 may not be a useful model for me on a day-to-day basis, I still think that GPT-3 is very interesting, and I think it's a very important piece of work that was performed. It's asking the question of what happens if we build a really big model? Where is that edge point? Have we detected it yet? I don't know, but I think this is an important step in learning more about natural language processing and learning more about transformer models and what they're capable of. I think there's a lot here to learn at an academic level, at an intellectual level, even if it's not a day-to-day tool that I would use. So that's it for me, guys. I hope that you have learned something. If you're still watching, if you have any comments or feedback, I'd love to hear from you. And I hope it was useful or informative. Thanks.